All right, my hypothesis testing experts out there, we are on the home stretch. We have one more lesson here in my video collection, lesson 8.6. Still continuing with our significance tests for a population mean, just kind of summarizing some important ideas and making an additional connection here at the end. So, important ideas. First, the mean of our sampling distribution is the same as the mean that we assume from the null hypothesis. Big note right here, it's a very common mistake to forget to recalculate, but for the standard deviation of our sampling distribution of sample means is calculated by taking your sample standard deviation and dividing by the square root of the sample size. So be very careful that you get that. You'll use that then to help calculate your test stat, which is a t-star value. So keeping that in mind there. The conditions to check, same as we talked about a moment ago in a previous video, our random condition and our normal condition. And the normal condition, we just have to meet one of these three. If they tell me the population is normal, I don't care how many they have in the sample. Sample of 3, sample of 3,000, it's all good. Sampling distribution is guaranteed to be normal. If they don't tell me that, now I'm checking the sample size. Do I have at least 30? If the answer is yes, fantastic. The central limit theorem tells us that samples of at least 30, when calculating the sample mean, will produce a sampling distribution of those sample means to be approximately normal. So we're good there. And if that's not the case, then the third option, last resort, I don't know the population is normal, my sample size is less than 30, so now I need to make a graph and compare, look for skew or outliers, and if there's nothing present that's obvious, we'll then go back and assume the population was normal, infer that from our sample graph, and then continue on. Next up will be our test stat, putting things together, our sample mean minus the mean we assumed, which is our sampling distribution sample center, and our standard deviation of our sampling distribution here gives us our test stat. We'll get our p-value using the table B, times 2 for the two-sided test, so just make sure you think about that. It's two-sided. And this additional connection I want to show today is that if you do run a two-sided test, the test matches the same as what a confidence interval would have produced. So if you'll see that kind of connection here, that a two-sided test coincides with a confidence interval. Now we'll talk about what percent confidence in a moment. Let's take a look at our example. Do our employees have high blood pressure? The health director of a large company is concerned about the effects of stress on the company's middle-aged male employees. According to the National Center for Health Statistics, the mean systolic blood pressure for males 35 to 44 years of age is 124. The health director takes a random sample of 72 male employees in this age group and records their blood pressures. The data have a mean of 126.93 and a standard deviation of 14.90. Question number 1, do the data give convincing evidence that the mean blood pressure for all the company's 35 to 44-year-old male employees differs from the national average? So my 4-step process, state, here's my null hypothesis. The mean is equal to 124. We assume it's the same as the national average. We're concerned that maybe this company is different than that, so the alternative is the mean is not equal to 124. Population mean is the true mean blood pressure for all males at this company. We only have a sample of 72 of them. I'm assuming this is a very large company and there are many, many more males in that age group than that. Our significance level will go with 0.05. If it does not specify, remember that's always going to be our go-to. So our plan step. Let's name the procedure. It's a one-sample t-test for population mean. Our conditions, checking the random condition, that's the easy one, they usually say it, and it does say in the problem they had a random sample of 72. Normal, got lucky on this one, sample size was 72, which is greater than or equal to 30, so again the central limit theorem applies. Now that the conditions are met, let's do this. So here's our sample mean and our sample standard deviation that was provided in the problem. The mean of the sampling distribution is 124. The standard deviation of the sampling distribution, as we assume that from the null, right, is our sample standard deviation divided by square root n. So samples of size 72 will typically vary by 1.76 from a mean of 124. Convert that into our test stat. We'll go, let's slide over a little bit, our sample value minus what we assumed, divide by our sampling distribution standard deviation to get our t-star value of 1.665. So now we go to the table. Now before I go to the table, technically I want a degrees of freedom of 71. But I'm going to have to deal with a degrees freedom 60 because 71 is not an option. And I never want to go up because I don't have at least that many. So I must go down to the one that I definitely do have. I do have at least 60. I don't have at least 80. So down to 60. Remember that number again. That was 1.665. So go across our 60 row, 1.665. Oh, we are close there. Just a little bit below 1.671 and above this guy here. So to the top to get our area in the tail, 0.05 to 0.10 is that tail probability. But since this is a two-sided test, try to cover that up for now, we were going to need to double that interval. So instead of 0.05 to 0.10, it's 0.10 to 0.20. So the p-value is between these two. All right, conclusion. Since the p-value, which is between 0.10 and 0.20, is greater than alpha, or 0.05, we fail to reject the null. We do not have convincing evidence that the male's blood pressure at this company differs from the national average. Okay, feel free to pause the video at any point here to go back and make sure you have all the details there. That's our formal four-step plan. So nothing really new from the previous example, just reiterating the fact that we have to double the area in the tail because of it being a two-sided test. Now here's the connection I wanted to make next, the connection to confidence intervals. So a 95% confidence interval. I'm not going to have us go back and actually recalculate like we did in the previous chapter, but if we made a 95% confidence interval out of the information that we had, these would be the bounds of the interval. So this would tell us that we are 95% confident that the true average blood pressure for males at this company in that age group is between 123.43 and 130.43. Now, let's think about how this compares to our results from the question above. Notice how we failed to reject the null. We didn't have convincing evidence that their blood pressure was different than the national average. The national average, again, was 124. So if we don't have convincing evidence that the national average differs from this, that means this must still be, or let me say that again, if we don't have convincing evidence that the employees, the male employees at this company differs from the national average, that means that this value must be a plausible value for the blood pressure of all of our male employees at this company. So if this is a plausible value, it would be in the confidence interval, which 124 is. It does not matter how close it is to one bound or another. That has nothing to do with it. It is only whether it is in the interval or is not in the interval. And since it is in the interval, it's plausible, and that coincides with the same conclusion we found here. We couldn't reject 124 because it's possible that their average truly is the same as the national average. Now, the connection to make. The direct connection between confidence intervals and hypothesis tests for the population mean is that if you're dealing with a two-sided test at our significance level of 0.05, the results will be the same as a 95% confidence interval. Now, that said, if I was dealing with a two-sided test and my significance level was 10%, that would correspond to a 90% confidence interval. Now, we can make a case for a one-sided test and confidence interval. It's not as direct. Like, it's like 5% 95, 10% 90. They directly relate that way. If it was a one-sided test and our significance level was 5%, that would actually correspond to a 90% confidence interval. I'm not going to get into that too much in this lesson. Just going to make the quick connection here. So, kind of summarizing what I had noted a moment ago, since the mean of 124 is a plausible value contained in our interval, it could in fact be the average for the males at this company. So our 5% significance level and our results here do coincide with a 95% confidence interval. So that's it. So I hope you enjoyed the lessons that we've seen here in hypothesis testing. This really does help to lay the foundation for a lot of statistical inference that can be done in further types of testing. But anyway, feel free to rewatch, pause, rewind, whatever you need to do for lesson 8.6 on page 12.